Hello everyone. In this video, we discuss a type of linear programming problem which we call assignment problems. What are assignment problems? Assignment problems are linear programming problems that are primarily concerned with determining optimal assignment or allocation of resources. It could be people assigned to tasks, jobs assigned to machines, contracts assigned to bidders, or salespeople assigned to areas. In an assignment problem, only one person is assigned to one task, one job to one machine, one contract to one bidder, and one salesperson to one area. The number of assignees and the number of tasks are equal, and each assignment problem has an associated opportunity cost table. Let us consider an example problem. An office has 4 workers and 4 tasks are to be performed. Workers differ in efficiency and tasks differ in their intrinsic difficulty. In the given table, the times each worker would take to complete each task are shown. How should the tasks be allocated to each worker to minimize the total man-hour? To solve the assignment problem, we shall use the Hungarian method, and here are the steps. First, given the original table or matrix, let us find the opportunity cost table of the problem. We subtract the smallest number in each row of the original cost table or matrix from every number in that row. In the first row, the smallest number is 8. So we get 8 minus 8, 20 minus 8, 15 minus 8, and 17 minus 8. In the second row, the smallest number is 10. So we get 15 minus 10, 16 minus 10, 12 minus 10, and 10 minus 10. In the third row, the smallest is 16. So we get 22 minus 16, 19 minus 16, 16 minus 16, 30 minus 16. And in the fourth row, the smallest number is 9. So we get 25 minus 9, 15 minus 9, 12 minus 9, and 9 minus 9. And then we get the following table. Then we subtract the smallest number in each column of the table obtained in step 1a from every number in that column. So in the first column, the smallest number is 0. So if we subtract 0 from all the numbers in the first column, we will get the same entries. In the second column, the smallest number is 3. So we get 12 minus 3, 6 minus 3, 3 minus 3, and 6 minus 3. And in the third and in the fourth column, the lowest number are both 0. So therefore, the entries in the third and fourth column will remain unchanged. The table obtained in step 1b is called the opportunity cost table. So we shall use that table in step number 2 to see whether an optimal assignment can be made. The procedure is to draw the minimum number of vertical and horizontal straight lines necessary to cover all the zeros in the opportunity cost table. If the minimum number of lines equals either the number of rows or columns, an optimal assignment can be made. If the minimum number of lines is less than the number of rows or columns, we proceed to step number 3. In our opportunity cost table, there are 4 rows or 4 columns. So if the minimum number of lines to cover all the zeros is equal to 4, an optimal assignment can be made. But if the minimum number of lines is less than 3, then that means we need to proceed to step number 3 and adjust the opportunity cost table. So in our example, we use the following line to cover the fourth column, and then to cover the third row, and to cover the first column. So using these 3 lines, we covered all the necessary zeros. So the minimum number of lines is equal to 3, which is less than 4. So in this case, the table is not yet optimal. So we need to proceed to step number 3. Since the opportunity cost table in step 2 did not provide an optimal solution, we need to revise the present opportunity cost table. This is done by subtracting the smallest number not covered by a line from every other uncovered number. The smallest number is 2, so we need to subtract it from 9, 7, 3, 2, 3, and 3. And that same smallest number is also added to any numbers lying at the intersection of the horizontal and vertical lines. So 2 will be added to 6 and 14. And this will be the resulting table. And then we return to step 2 and continue the cycle until an optimal assignment is possible. Now, to test again for optimal assignment, we return to step number 2 and find the minimum number of lines necessary to cover all zeros in the revised opportunity cost table. In this case, we cover the fourth column, the third row, the first column, and then the second row. Now in this case, the minimum number of lines needed is 4, which is already equal to the number of rows or columns of the opportunity cost table. So this indicates that the opportunity cost table shows an optimal solution. Now we can proceed to step number 4. Step number 4 includes making the allocation. So we note that only one assignment will be made from each row or column. We use this fact to proceed to making the final allocation as follows. So first, we need to find a row or a column that contains only one zero entry. And then make the assignment corresponding to that zero cell. And then eliminate that row and column from the table. And then continue until all the assignments have been made. So let us consider again the revised opportunity cost table. So in here, we see that row 1 has 1 0. And this means that task A is to be assigned to worker number 1. So we shall remove row A and column 1. And then, from the remaining entries, D, or the fourth row, has 1 0. So that means task D is to be assigned to worker number 4. So we will remove row D and column 4. And then from the remaining entries, B has 1 0 and it will be assigned to worker number 3. So which means that we will remove row B and column 3. And this leaves us with C being assigned to worker number 2. Now to determine the minimum total man-hour, we use again the original table or original matrix of the problem. Since task A is assigned to worker 1, it gives us a value of 8. Task B is assigned to worker 4, we have a value of 9. Task D is assigned to worker 3, we have a value of 12. And task C is assigned to worker 2, and we have a value of 19. Now adding all these values will give us the minimum total man-hour, which is 48. The previous problem is a minimization problem. Now this time, let us consider a maximization problem. At the head office of a certain company, there are 5 registration counters and 5 persons are available for service. To which counter should we assign each person so that profit is at its maximum? The steps in solving the maximization problem is pretty similar to solving the minimization problem. We just need to add one step at the beginning. So we need to convert the problem into a minimization problem by subtracting each entry from the highest value in the given table. The highest value is 70, so each entry will be subtracted from 70. From the resulting table, we follow all the steps in the minimization problem. We subtract the smallest number in each row from every number in that row. In the first 4 rows, the smallest number is 22, and in the 5th row, the smallest number is 0. Subtracting the smallest numbers in the entries in their corresponding rows, we get the following table. Then, we subtract the smallest number in each column of the resulting table from every number in that column. In the first column, the lowest number is 0. Second column, the lowest number is 0. Third column, the lowest number is 0. Fourth column, the lowest number is 4. Fifth column, the lowest number is 0. So, in the first, second, third, and fifth columns, the entries will remain unchanged. But for the fourth column, we need to subtract 4 from every other number in that column. And the resulting table is the opportunity cost table. And then we check for optimality by determining the minimum number of lines needed to cover all the zeros in the table. So for optimal solution, there should be 5 number of lines to cover all the zeros. But in this case, we can only use 4 lines to cover all the zeros, which is less than 5. And this means that the opportunity cost table is not yet optimal. Therefore, we need to revise that table. Again, to revise, we subtract the smallest number not covered by a line from every other uncovered number. The smallest number is 4. So we get 16 minus 4, 13 minus 4, 15 minus 4, 4 minus 4, 8 minus 4, 7 minus 4, 6 minus 4, and 5 minus 4. That same number 4 will be added to the intersection of the lines. So we have 10 plus 4, 15 plus 4, 33 plus 4, and we get the following table. Now we check again for optimality by determining the minimum number of lines needed to cover all the zeros. Now this time, we will need 5 lines to cover all the zeros. And this means that this revised opportunity cost table is now optimal. And we can now make our allocation of counters to each of the 5 persons. To make an allocation, we find a row containing only one zero. In this case, counter 3 has 1 0 and corresponds to person A. So which means counter 3 is assigned to person A. Now in the remaining entries, counter 2 now has 1 0 and counter 2 will be assigned to person E. And then from the remaining entries, counter 1 now has 1 0 and counter 1 will be assigned to person C. And then from the remaining entries, counter 4 now has 1 0 and counter 4 will be assigned to person B. And then lastly, of course, counter 5 will now be assigned to person B. Now using the original table or original matrix, we shall now determine the maximum total profit. Since counter 3 is assigned to person A, profit is 48. Counter 2 is assigned to person E, the profit is 44. Counter 1 is assigned to person C, the profit is 48. Counter 4 is assigned to person D, the profit is 44. And counter 5 is assigned to person B, the profit is 70. Now, getting the grand total, then we get the total profit of 254. So this is the solution for the maximization problem. Now, thank you for watching this video and don't forget to subscribe to my channel. Thank you very much.